Hello everyone, thank you for taking your time to listen to my talk. My name is Katarina Moravkova. I'm a PhD student in the School of Psychology and Neuroscience at the University of Glasgow, and today I will briefly talk to you about my project, which investigates coarse-scale orientation tuning in the human visual cortex. Now, this work has been motivated by years of research of animal neurophysiology in the field of visual neuroscience, in which receptive field profiles have been described with more simple models, such as simple two-dimensional Gaussian functions, to more complex functions, such as Gabor filter functions. And particularly in Ringach 2002, there has been a division of receptive field profiles as described by Gabor filter functions according to the phase of the Gabor filter functions, dividing these into even symmetric and asymmetric Gabor filter profiles as determined by the organization of the inhibitory and the excitatory regions within the Gabor filter function. Now, in functional magnetic resonance imaging, there have been multiple attempts to use these findings, which have been shown at the level of single neurons, and apply them at the level of a voxel. One of these approaches is the population receptive field, or pRF model, introduced in 2008 by Dumoulin Wandell, which have described visual responses by the use of two-dimensional Gaussian functions. Now, quite recently, in 2012, Suiterban et al. Have introduced an extension of this pRF model in which they attempted to capture the center-surround organization of receptive fields, which has been shown at the single neuron level, obtaining an improved performance both qualitatively and quantitatively when describing fMRI signal driven by visual stimulation. Now, if we look at the signal that we obtain when we present participants with visual stimulation, we can describe our data with many different models and many approaches. In the pRF model, for each voxel, we obtain the position and the size of this pRF when we obtain our predicted time series. Now, imagine the pRF model would be a Gabor filter function. In this case, for each time series, we would obtain 3 additional parameters when developing our predictions, and that is the angle, the phase, and the spatial frequency, which in this case, in this talk, I'm going to focus on the relationship of angle and phase and its relationship to the even symmetric and asymmetric profiles that we can observe in the data. Now, for our modeling approach in this case, we are very much inspired by the simple or the conventional pRF model, but in our case, our underlying pRF is modeled as a Gabor filter function, and as I said before, it allows us to fit 3 additional parameters of angle, spatial frequency, and phase at a single voxel level. Now, after we have multiple predictions with many different combinations of these parameters, we calculate the overlap for each modeled or modeled pRF with the stimuli sequence that we would afterwards present to participants in the fMRI scanner. In this case, it is the moving bar stimuli. Afterwards, we convolve this with the hemodynamic response function, which allowed us to obtain multiple predicted time series with many different combinations of parameters, which afterwards we can compare with the data with which we obtain in the scanner when participants are engaged in the moving bar visual task. Now, for any technical details, please feel free to contact me at your own time. So first of all, when we look at our model, we wanted to know how does its performance compare to the simple or the conventional pRF model. So firstly, we looked at how this model allows us to reconstruct retinotopic maps. And we can see that our Gabor filter model reconstructs them quite accurately. However, in the later areas of the visual system hierarchy, there seem to be some deviations. Secondly, we wanted to know if we can recover the size by eccentricity relationship in which the size of the pRF or receptive field increases with eccentricity. And once again, we obtain this measure relatively well. However, there are some deviations in the slopes and intercepts between the two models. And again, if you're interested, feel free to follow up on this at your own time. Thirdly, we wanted to compare these models quantitatively, and what you can see in these results for both adjusted R-squared and AIC, that there seems to be a relationship between the pRF shape, which in this case we would refer to the even symmetry, simple or odd symmetry of the pRF, and we see that the even symmetric Gabor filter function pRF describes most accurately or with the best performance the signal that we measure. Lastly, we wanted to know if we see any qualitative improvements, and in this case I'm showing example time series for two visually responsive voxels, and as you can see by indicated by the arrows, there are multiple events in which the Gabor filter model seems to capture the signal a bit more accurately. So after we established that the model seems to be working relatively well, we wanted to know the following. Firstly, if there are any spatial patterns in the organization of the edit parameters, such as angle and phase, if these patterns emerge due to a modeling bias, or if they are driven by a physiologically relevant signal. And lastly, we wanted to know if we can recover any patterns using different types of visual stimulation. So for the first question, let's look at the results. So in this case, I'm showing you data which have been filtered for fits which were fitted using an odd symmetric Gabor filter pRF. These are data for one subject filtered for the early visual area V1, and I'm showing the results of voxels in the visual space, and the color ranging between 0 to 360 degrees shows the angle which was used to fit the Gabor filter pRF. Now, as you can see, we already start to see some pattern emerge for this subject, and we look at the results pulled across all visual areas. We see a split between the upper and lower visual field. Now, if we look at the results for all subjects pulled across all analyzed early visual areas, we see a full representation of angular tuning in space ranging from 0 to 360. Now, if we compare these results with the results for the even symmetric Gabors, we see that there appears to be a slightly different pattern. In this case, I'm showing data for one subject filtered for early visual area V3, and the Gabor filter pRF angle parameter now ranges between 0 and 180. And we start to see a more quadrant representation, which gets more pronounced if I show you the results for the for one subject, and if I show you the results for all subject pool across all visual areas, we see there is a clear split between the two diagonals, showing us that in the upper right and lower left we have fits which are centered on 135 degrees, and in the upper left and lower right we see fits that are centered at 45 degrees. Now, these effects appears to be phase dependent, and moreover we see that it replicates at an individual subject level, and we can also cross-validate it across MEMS. Now, after we established this, we wanted to know, is this driven by a modeling bias? And for this, we developed robust simulation protocols in which we generated multiple null distributions of orientation tuning in space across different levels of noise. So no organization was present at all, and we wanted to know if we fit the same model as before, do we obtain the same results, highlighting that there might be a modeling bias, or can we recover angle parameters accurately? And when we look at the results, we see that for the asymmetric Gabors, we see a very similar pattern across all levels of noise, highlighting that this result seems to be sensitive to a modeling bias, while for the fits which were fitted with the even symmetric Gabors, it does not seem to be the case, highlighting that this might be driven by something physiological. Now, lastly, we wanted to know, can we replicate this using different types of visual stimulation? And for this case, we used the data from the Connectome Project, which were collected using the rotating wedge and expanding contracting ring stimuli. And once again, we replicate the results for both the odd symmetric Gabor filter fits and the even symmetric Gabor filter fits. So, suggesting that we have to summarize, we can see that we obtain coarse-scale topography of orientation tuning using our newly developed model. We also see that one part of our result is driven by the modeling bias, while the second might be driven by something physiological. And finally, we see that we can replicate this in a different type of visual stimulation, highlighting that the results for the even symmetric Gabors might be related to some behavioral results, such as introduced by Sasaki in 2008. So thank you very much. These are my acknowledgements, and thank you for your attention. And please feel free to message me if you have any questions. Thank you very much.